If a narrow beam of green light strikes a shallow dish of cool water, vapor begins to lift from the surface. There is no heating element and no boiling metal underneath. But as vapor escapes, the air directly above the water cools instead of warming. This cooling air challenges the traditional understanding of evaporation. The standard model suggests that heat makes molecules move faster until the most energetic ones near the surface break away from their neighbors. Temperature is simply the measure of that molecular motion. This thermal explanation is the backbone of thermodynamics. It is the physics behind drying clothes, shrinking puddles, and the massive cooling towers used in industrial power generation. If evaporation were driven strictly by heat, that energy should show up as a rise in temperature before it tears molecules away. In these experiments, however, the thermometer refuses to rise. This equation is nature's financial ledger. To evaporate a kilogram of water, you pay a specific energy called latent heat. Under ideal sunlight, this math creates a ceiling. A perfect solar evaporator only removes 1.5 kilograms per square meter hourly before running out of heat. When solar evaporation experiments at MIT began reporting rates far beyond this limit, the data suggested the ledger was no longer balancing. Using partially wetted hydrogels, the team recorded evaporation exceeding the thermal ceiling by 5 times. A hydrogel is a molecular sponge. Because evaporation happens where water meets air, the hydrogel's internal surfaces fold that boundary into countless microscopic pockets, amplifying effects that might be invisible on a flat surface. The researchers faced a stark choice. Either the energy accounting was flawed or an unknown force was at work. The team began by searching for measurement errors. They checked for hidden heat absorbed from the environment, shifted humidity levels, and errors in mass loss. To rule out the hydrogel material itself as the cause, they moved the experiment to ordinary flat water and curved droplets. The high evaporation rates persisted. Testing different colors of light revealed a peak. Evaporation spiked at 520 nanometers in the green spectrum. Since bulk water is nearly transparent to these wavelengths, the energy isn't swallowed by the liquid, but acts specifically at the air-water boundary. The rates also changed based on orientation. The effect was strongest when the light beam struck the water surface at an angle of 45 degrees. Finally, they found that the effect responded to the orientation of the light's electric field, peaking under transverse magnetic polarization. These sensitivities to color, angle, and polarization point away from simple heating and toward a discrete event occurring at the interface. At the air-water boundary, molecules arrange into shifting clusters held by hydrogen bonds, creating an uneven electrical environment. A photon carries energy and momentum. Its electric field can exert enough force on these clusters to cleave them away from the liquid surface. This direct liberation of clusters is the photomolecular effect. The observation draws a parallel to the 1880s, when Heinrich Hertz discovered that light striking a material could eject electrons. Albert Einstein later explained that light acts as a particle, proving that photons can trigger discrete physical escape events. While the photomolecular effect involves water clusters rather than electrons, the underlying physics is similar. Under these specific boundary conditions, visible photons become an active mechanical force, physically liberating matter from the liquid. The implications of these microscopic interactions extend to any system dominated by water boundaries. This includes fog, which is essentially a suspended field of highly curved air-water interfaces. If visible photons can knock clusters from droplet surfaces, then the boundaries inside clouds and fog are more optically active than bulk water models suggest. MIT tested this in an artificial cloud chamber, observing that fog could be heated by visible light, despite the weak absorption of water in that spectrum. Because clouds both reflect sunlight and trap heat, even small changes in droplet behavior can scale into large atmospheric consequences. This interaction represents a new variable in climate modeling and forecasting. By focusing primarily on bulk absorption, models may be overlooking a surface-level interaction that alters how energy moves through the sky. In industry, evaporation is a massive energy drain. The process of drying everything from paper and textiles to food and chemicals consumes roughly 20% of all industrial energy usage globally. A non-thermal evaporation pathway could potentially reduce the need for massive, energy-intensive furnaces and heat exchangers, replacing them with light-based systems. Solar desalination could also be reimagined. Instead of using black absorbers to create heat, a photomolecular still would be designed to optimize the wavelength, angle, and polarization of the incoming light. However, a lab-scale discovery faces a difficult path to commercialization. In the field, microscopic dirt and dense salt crystals can rapidly clog a porous membrane, destroying the precise interface needed for the effect to work. Scaling this technology requires maintaining optical alignment across a full day and managing the brine produced by desalination. The mechanism must also be verified through independent laboratory replication. Heat is not the only driver of evaporation. The liquid surface is not merely a passive door. It is a complex boundary where light can act directly, revealing how much we have yet to learn about the most common processes around us.